Okay, in this lecture video, we're going to start off where we left off in the last lecture video, and that's with this second example in this section. So it says that a sample of size 19 drawn from a normally distributed population has a sample mean of 43 and a population standard deviation of 12. Construct an 80% confidence interval for the population mean and interpret your results. So just like we've done with the last couple of problems, the first question I'm always going to ask you is, how do we know that this is a Chapter 7 question? Like we were saying in the last video, whenever we see a question that asks us to construct a confidence interval, we know that that must be a Chapter 7 question. Like I said in the last video, there's a couple of concepts that we're also going to learn in addition to creating confidence intervals. But the bulk of Chapter 7 deals with confidence intervals. So therefore, if you see that it's a confidence interval question, you know that we're dealing with a Chapter 7 question. Whenever we're dealing with a Chapter 7 question for estimation, whenever we start off these problems, we start off by asking two questions. And those two questions are, is n greater than or equal to 30? So is our sample size greater than or equal to 30? And is sigma known? That's how we've started off all of these questions so far, with these two questions. Alright, is n greater than or equal to 30? Is our sample size greater than or equal to 30? Here it says that we have a sample size of 19, so therefore for this one we're going to say no, and that little n is equal to 19. Then the next question is sigma known? Sigma is our population standard deviation. And here it says that the population is normally distributed and has a mean of 43 and a population standard deviation of 12. So therefore we do know our population standard deviation, and sigma is going to be equal to 12. Since we answered yes to at least one of these questions, in order to create a confidence interval, we know that we can always fill in the bare bones of this right here. Right, this is the bare bones for our confidence interval. But since we answered yes to at least one of these questions, we're going to use z sub alpha divided by 2 right here. If we answered no to both of these questions, then this right here would be t sub alpha divided by 2. But as long as we answer yes to at least one of them, we get to use z's right here instead. Lastly, we're always going to fill in our standard deviation up here in the numerator. If we know sigma, we're going to use sigma. If we don't know sigma, then we would have used s, the sample standard deviation, here instead. So now we have our formula for our confidence interval. So let's try filling in some numbers. We know that x bar is the sample mean, and the sample mean in our problem is equal to 43. I'll skip z sub alpha here for a second, alpha divided by 2 for a second, because I can fill in what sigma is equal to, and I can also fill in what our sample size, little n, is equal to. So now we just need to figure out what z sub alpha is, and then we can do some arithmetic, find our interval, provide our interpretation, and we're going to be done. So let's find z sub alpha divided by 2. Since we're looking for z's, we know that we're going to be using a bell-shaped and symmetric distribution. More specifically, it's our standard normal distribution. Our confidence level for this interval is 80%, so therefore 80% is going to go between those two cutoffs. Since that's our confidence level, what's the formula that we use for our confidence level? The formula for our confidence level is 1 minus alpha. So 80% is equal to 1 minus alpha, which means that alpha is equal to 20% or 0.2. Right? Alpha is just simply what's left over between our confidence level and 100%. Or if you do the arithmetic here and solve for alpha, you'll get that alpha is equal to 20% or 0.2. So since this is a symmetric distribution, we're going to put 10% right here and 10% right here so that these percentages add up to 100%, right? If in between these two cutoffs we have 80%, then here we have to have 10% and here we have to have 10% to get this up to 100%. And again, remember that it's a symmetric distribution. So therefore, if this is 10% and alpha is 20%, then 10% is the same thing as half of alpha, or alpha divided by 2. Which should make sense then that here these cutoffs we're calling z sub alpha divided by 2. And now if we want to figure out what these z values are, that's what we're trying to figure out so we can plug it into this spot right here. What we're going to do is we're going to go looking for the z value in our z table that corresponds to 10%, right? We have 10% in this tail right here. So let's do it. If we go to our z table and we go looking for 10%, remember that percentages are here in the body of our table, and the percentages are given as decimals. So therefore, if we're looking for 10%, we're going to look here in the body of this table, and we're going to look for 0.1. And if you look for 0.1, the closest that we're going to get to is here, 0.1003. That's the closest that we're going to get to 0.1. Now, if we follow this outwards, we're going to see that the z value is negative 1.28. So we can use the z value, the z sub alpha divided by 2, as 1.28. Again, remember that the way that I describe the z sub alpha divided by 2's is the way is that I'm going to always call them positive values. Now keep in mind that here the z value is going to be below the mean, so therefore technically this one's going to be a negative, and this z value is going to be above the mean, so technically it's positive. But for the sake of explaining stuff, especially once we get to chapter 8, I'm going to use these z sub alpha divided by 2's. I'm going to describe them as positive values. Either way, whether you choose the positive value or the negative value, the arithmetic doesn't change, because here we're adding and subtracting that. You can add and subtract a positive number or add and subtract a negative number, and it still remains the same. Alright, but one other thing that I want to point out here is this. And we've talked about this briefly, but we also, since we've talked about this the last time, we've also introduced a new table. So there's some new stuff that we can do now. And that's this. Like we said before, we wanted to get to 0.1. Here we're a little bit off from 0.1. So technically what we said before is that the z value that we're looking for is somewhere between 1.28 and 1.29. If we had some z value between 1.28 and 1.29, then we could have the value 0.1, which is in between these two values right here, right? 0.1 or 10% is somewhere between these two values. So therefore, the z value that we're looking for is somewhere between 1.28 and 1.29. Well, what we can now do, if we want to have a more accurate z sub alpha divided by 2, i.e. having a third decimal place, we can use our t-table. So let's think about this here. Now, why can we use our t-table? Let me briefly just refer back to this graph that we've looked at before. And remember that in this graph that I said before, I said that here these different bell-shaped and symmetric curves, the ones that were already in the notes, these are different t-distributions. And the t-distributions are different because they have different degrees of freedom. But if you remember from what I said as the degrees of freedom get larger and larger and larger, these t-distributions get closer and closer and closer to our normal distribution. Well, our t distributions, this is what's giving us our t values. And our normal distribution, this is what's giving us our z values. Technically, it's our standard normal distribution. But either way, as our degrees of freedom get larger and larger and larger, we start to get closer and closer and closer to this z value that we're looking for. So, if we take that back to our graph now, if we take that back to our table now, if we keep increasing our degrees of freedom, and our degrees of freedom get larger and larger and larger, if we keep on going to the back side of this table, we can see that over here in this left-hand column, our degrees of freedom keep getting larger and larger and larger. All the way to the fact we're down here in this very, very, very last row. It says now that our degrees of freedom are infinity. So when our degrees of freedom are infinity, our t distribution has now converged to our normal distribution, our standard normal distribution. So therefore, another way of saying that is this. All of these values right here, these are all t values. Remember that in the body of the t table, all of these values are not percentages, they're t values. Except for this very, very, very last row right here. Since we have reached the degrees of freedom going all the way up to infinity, this last row, these are z values, which is why it also tells us that right here in this box, that hey, our degrees of freedom have reached infinity, so therefore these are now z values. So the cool thing is this, we have a couple of z values right here, and the neat thing is that these z values go down to not 2 decimal places, but they go down all the way to 3 decimal places. So we can get a 3rd decimal place for some z values. Now, if we go back to our z table, right, remember that this first row this first column along with the first row, they make up z values. So here we have a lot of z values. And on the other page, we have a lot of z values. So we have many more z values here than we have right here. Here, it just gives us a few z values. Now, why does it pick out these few z values? Well, remember from what we said above, that here these t's, they have subscripts. And what we said in the last lecture video is that you can imagine that these t subscripts are the same thing as these alpha divided by 2's that we're looking for. So therefore, if we go all the way down to the bottom row, you can think of these as being z values for certain alpha divided by 2's. And the alpha divided by 2's that we're choosing happen to just be really, really commonly used alpha divided by 2's. Here, for example, it's 20%, 10% for 0.1, 5% for 0.5, 0.025 for 2.5%, and so on and so forth. So here we're just using some common alpha divided by 2's. And for these common alpha divided by 2's, we have z values now to the 3rd decimal place. So let's go back to the problem that we're working on. Here we said that our alpha divided by 2 was equal to 10%, which is just the same thing as 0.1. So here, if our alpha divided by 2 is equal to 0.1, what we can now do is go to our t table and find the column that has the alpha divided by 2 of 0.1. And that's this second column right here. Here we have 0.1 as our alpha divided by 2. Now, if we follow this all the way down to the bottom, we get that the z value is 1.282. 1.282, which, going back to what we looked up in our z table before, that gives us our third decimal place. We now know that our third decimal place, right? Here, we said that we were off by a little bit, and we wanted something between 1.28 and 1.29. And now from this t table, we can find that the third decimal place is 2. So then now this corresponds to exactly 0.10. So therefore, now that we can look up some z values in our t table, whenever we can look up z values in our t table, we're going to use our t table to find those z values. So now here for this, we're not going to use 1.28 or 1.29. Instead, what we're going to do is be as accurate as we can and use 1.282. Alright, so if you use 1.282 and you do this arithmetic, you're going to get that this comes out to 39.47 to 46.53. Now, if you just use 1.28 or 1.29, the numbers that you're going to get are going to be slightly off, right? For your interval, you're going to have slightly different decimals here, which, generally speaking, is no big deal, as long as here we're looking at z values. However, I want to say two things about that. One is you should get in the habit of, if you can look up the z values on the t table, you should look up the z values on the t table. And again, as long as we have very commonly used alpha divided by 2's, we can use this t table to do that. The second thing is this. If this is a t value, sometimes the answer choices on the homework, the exams, and also on the final exam are very, 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 very close to each other. So that if you should be using a t value here, but you use a z value instead, the decimals are going to be really, really close to each other, so that will lead you to selecting the wrong answer. So, what I recommend is that if that's still a little bit fuzzy for you, rewind the video, see how we answered number 2 again, and we're also going to practice this in the next examples. But make sure that you're very, very familiar with how to use the t table and when to use it. Alright, let's go on to the next example. Here we have the next example in the notes, and this example says, a sample of size 12 students drawn from a large normally distributed population has a sample of mean 2.71 and a sample standard deviation of 0.51. Construct a 90% confidence interval for the population mean and interpret your results. Alright, as always, how do we know that this is a Chapter 7 question? It says confidence interval in it. How have we always started these Chapter 7 questions? So far, we've always started them with, is n greater than or equal to 30, and is sigma known? We've always started them with these two questions. Now, let's answer these questions. Is n greater than or equal to 30? Little n again stands for our sample size. Here it tells us that we have a sample size of 12, so therefore the answer to that is no, n is equal to 12. Is sigma known? Again, sigma is our population standard deviation. Here we're being told that our sample standard deviation is 0.51. So again, here The answer to this is no, and our sample standard deviation is given to us by S, and S is equal to 0.51. We're trying to construct a confidence interval, and the bare bones to our confidence interval that we can always write is always this, right? Because here so far, our confidence intervals have always dealt with the mean. So therefore we have x bar plus or minus something right here times our standard deviation divided by the square root of n. We just need to figure out what are we using here. Well, since we don't know sigma, we're going to use our sample standard deviation s instead. And now, what's most important is that we answered no to both of these questions. And because we answered no to both of these questions, here we're going to be using t sub alpha divided by 2 instead. So we're not going to use z, but we're going to use t instead. And again, why are we using t? If we go back to this decision rule table, again, we're asking ourselves whether or not n is greater than or equal to 30. We answered no. We answered whether or not sigma is known, and we answered no, sigma is unknown. And that's the only way that we can get down here to using t's. The only way that we can get to using t is if we answer no to both of those questions. In every other case, we're going to use z values. So that's why we're using t. While we're here, I also want to point out another concept, and I said I'd get back to this later, and that's this. If n is strictly less than 30, then here the central limit theorem doesn't apply. So therefore, we have to make the assumption that our population is normally distributed. That's this other caveat that I put in a box earlier, and I said that for right now, this is not super important. But now that we're doing an example on this, I'll point out that whenever we have this scenario, it's always being told to us that our population is normally distributed. So, if you look at all the examples that we're doing where we're going to be using t values, or more specifically when our sample size is less than 30, it always also includes that caveat in the wording of this problem that our population is normally distributed. Alright, but anyways, let's get back to answering this question. Here now we have our formula for our confidence interval. Let's try to plug in some values. Here it says that our sample mean is equal to 2.71. We'll skip this t sub alpha divided by 2 thing here for a second, because we know that s is equal to 0.51 and our n is equal to 12. So let's try to figure out what our t sub alpha divided by 2 is. Again, in order to look up this t value, we need to know two things. We need to know both what our alpha divided by 2 is, so we can tell which column that we're in, based off of these subscripts, right? Remember that those subscripts are alpha divided by 2. And we also need to know how many degrees of freedom that we have, so we can figure out which row that we're in. So let's do that. Let's figure out what our alpha divided by 2 is, and let's figure out what our degrees of freedom are. So here we have a 90% confidence interval. I'm hoping that it's becoming a little bit easier for you now to figure out both what alpha is equal to and what alpha divided by 2 is equal to. But let's do it here together one more time, just in case you're still a little bit fuzzy on it. We have a 90% confidence interval. Therefore, our confidence level is 90%. Therefore, between these two cutoffs, we're going to have 90%. The formula for our confidence level is given to us by 1 minus alpha. So therefore, alpha is equal to 10%, which is what's left over between our confidence level to 100%, or simply just 0.1. Since here we have 5% and here we have 5%, since it's a symmetric distribution that has to equal 100%, we can see that here 5% is the same thing as half of alpha, or 0.05. Same thing over here, we have alpha divided by 2, which is just the same thing as 0.05. So therefore now we know that our alpha divided by 2 as a decimal place is 0.05. The only thing that we still need to know is how many degrees of freedom do we have. What was our formula so far for the degrees of freedom? We said that the formula for degrees of freedom was equal to little n minus 1. And remember that here, we talked about that earlier in this decision rule box. The only time that we're really concerned with degrees of freedom is whenever we're using our t values. So therefore, the way that we calculate out our degrees of freedom, or abbreviated as df, is to take little n minus 1, where again, little n is our sample size. So therefore, we're going to take little n minus 1, or sample size minus 1. We already said that our sample size was equal to 12. So 12 minus 1 might be the simplest thing that we do all day today. 12 minus 1 is equal to 11. So now we know that our alpha divided by 2 is equal to 0.05, and our degrees of freedom is equal to 11. Now we can go back to our to our t table. Our alpha divided by 2 is equal to 0.05, so we know we have to be in this column right here, the third column of t values. And our degrees of freedom is equal to 11, so we know we're going to be in this row. So therefore, the t value that we're looking for is 1.796. Again, remember that unlike the z table, in the body of the t table, all of these values are t values, they're not percentages. So therefore, our t value is 1.796. So therefore, the value that we're going to put right here is 1.796. And bam! We're just down to arithmetic now. If you do the arithmetic on this, I'll spare you the arithmetic. We get 2.45 to 2.97. Again, like I said in a previous lecture video, doesn't matter whether or not we have square brackets here or the round brackets or parentheses, whatever you want to call them. Since we're dealing with a continuous random variable, t values are also continuous random variables. The probability of omitting exactly one continuous random variable is equal to 0. Let me rephrase that. The probability of exactly one continuous random variable, obtaining one continuous random variable, is equal to 0. Since we're just omitting one here by making this from a round bracket from a square bracket to a round bracket or vice versa, we're just changing it by a probability of 0. So therefore, our confidence level remains unchanged. The other way of saying that is, it doesn't matter if you write it as square brackets or round brackets. The last thing that we need to do now is provide our interpretation. And our interpretation is that we are 90% confident that the true population mean mu is in the interval 2.45 to 2.97. Again, remember, if you remember this sentence, the only thing that's ever going to change in this sentence is what I'm putting in these boxes right here. And we're definitely going to get to that, right? The two things that we've changed so far has been this first box and this last box. We haven't changed the population mean mu, we're always going to be looking for the population, right? Remember that we're always estimating something from the population. We're never estimating something from the sample, which is why I'm not including the word population inside this box. Remember back to that very first picture, we calculate something out from the sample. We know this number. We're using this to estimate something from the population. So therefore, what we're estimating is always going to be something from the population. Here, it just happens to be that we're estimating the mean. Later on, we're also going to estimate the population proportion. So here it's going to change to proportion P. And once we change to proportion P, we're also going to see that we're going to slightly change how we begin those problems. But we haven't gotten there yet. Here we still have another example to do. So let's do this last example. And I'm going to change up this example here a little bit. Instead of 50, I'm going to change this right here to 15. So instead of 50 randomly selected individuals, I'm going to say that it's 15 randomly selected individuals. All right, so 15 randomly selected individuals were timed completing a tax form. Oh gosh, that sounds horrible. Wow, I hope they paid them. The sample mean was 23.6 minutes. The sample standard deviation was 2.4 minutes. Construct a 99% confidence interval for the mean time required by all individuals to complete the form and interpret your results. Oh gosh, I feel like I have to change this example for next semester. Alright, right? Nobody wants to talk about doing taxes, right? I feel like my palms started sweating a little bit just reading this problem. Anyways, as always, how do we know that this is a Chapter 7 question? Because it says confidence intervals. And so far, how have we always started our confidence interval questions? By asking those two questions. Is n greater than or equal to 30, and is sigma known? So let's answer them. Is n greater than or equal to 30? No, that's a part that I changed. I said that we're going to deal with 15 randomly selected individuals. So therefore, I changed n to be equal to 15. And do we know our population standard deviation? The answer to this is also no. Because here it says that a sample mean was this, and a sample standard deviation was this. So therefore, S is equal to 2.4 minutes. The bare bones that we're always going to use to calculate out our confidence interval is this formula right here. Now we just need to figure out what we're going to put up here in our numerator. Our numerator is always going to have the standard deviation in it. If we know sigma, we're going to use sigma, but we don't know sigma, so here we're going to now use the sample standard deviation S instead. And most importantly, since we answered no to both of these questions, we're going to use T sub alpha divided by 2 here. Again, the only time that we use Z sub alpha divided by 2 here is if we answer yes to at least one of those questions. It doesn't matter which one, but we have to answer yes to at least one of them. One of them, the other, or to both of them. Alright, so here we have our formula that we're going to use for our confidence interval. We can start plugging values into this. It says that the sample mean, which is x bar, is equal to 23.6. We'll skip over T sub alpha divided by 2 here for a second, because we know that S is equal to 2.4 and our sample size is equal to 15. Now we just need to figure out what T sub alpha divided by 2 is. And again, remember that the two things that we need to know to determine what our T value is we need to know what alpha divided by 2 is, and we also need to know how many degrees of freedom that we have. So let's first figure out what alpha divided by 2 is. You can probably do this in your head by now, but I'll do it here just for completeness anyways, just in case you're still struggling with this a little bit. We have a 99% confidence level, so therefore 99% is going to go between these two cutoffs. The formula that we're going to use for our confidence level is 1 minus alpha. So therefore, if you solve for alpha, alpha is equal to 1%, which is just the same thing as 0.01. If we have 99% in here, that means that we're going to put 0.5% over here and 0.5% over here, which if alpha is equal to 1%, again, this is alpha divided by 2, and this is alpha divided by 2. If we write alpha divided by 2 as a decimal place, we get that it's 0.005, right? Remember that 1% is 0.01, so therefore 0.5% is 0.005. So now we know that our alpha divided by 2 is 0.005. Now what we still need to do is figure out what our degrees of freedom are. And our degrees of freedom is again what we're going to abbreviate by DF for degrees of freedom. And what's our formula for the degrees of freedom? It's little n minus 1. And again, little n stands for our sample size. We said that our sample size was equal to 15. So 15 minus 1 is equal to 14. So now we know that we have 14 degrees of freedom along with our alpha divided by 2 being 0.005. We can now go to our T table. Come over here to the column that has the correct alpha divided by 2 subscript, which is 0.005. We can then follow it down to where we have 14 degrees of freedom, and we get the T value of 2.977. So here's our T value of 2.977. So therefore we can plug that T value 2.977 into this spot in the formula. If we do the arithmetic on this, this will come out to 21.76 and 25.44. The last thing that we need to do is provide our interpretation, and our interpretation says we are 99% confident that the population mean mu is in the interval 21.76 to 25.44. Alright, I'm hoping that these are getting to be a little bit easier for you. And I want to mention a couple of things before we go on to the next section. Because the next section we're going to start to do some things that are a little bit different. So I first want to point out a good test-taking tip that I can give you. And I also want to start to tell you a little bit about how things are going to be a little bit different in the next section. So let's start off with the test-taking tip. This test-taking tip is not going to only help you out for the common final exam, but this test-taking tip is also going to help you out for the exams in this class and also for the homework. And the test-taking tip is this. On past common final exams, and remember that your homework questions and your in-class exam questions that you take throughout the semester are just recycled past common final exam questions. And one of the things that's true for these past common final exam questions is this. if you have this as your lower bound for your confidence interval, if this is the correct lower bound, you're never going to see another answer choice that has the correct lower bound, but an incorrect upper bound. So another way of saying that is this. Suppose this is answer choice A on your exam. What you will not see is that answer choice B will have this number as being the same, but this number as being different, say 28. You will not see this. You will only see that, suppose you'll see like an answer choice C, where this is like 22 and this right here is 28. Right? You will never see two answer choices where one number is correct for both of them and one number is correct only for one of them and the other one has an incorrect number. You will never see something like B. You will only see answer choices that are like C, where both of the numbers are incorrect. This is something that's been true for the last couple of years on the Common Final Exam. So why am I telling you this as a test-taking tip? Well, here's this. You're always doing this arithmetic right here, where you're taking this number and you're adding this to it, and then you're taking this number and you're subtracting this from it. Well, if you only do one of those, say you take this number and you subtract this from it, it's going to give you the correct value. There's no sense in also finding the other correct value if you can just use this number to figure out which answer choice is the correct answer choice. That'll save you a couple of seconds. Granted, it might only save you like 10 or 15 seconds or whatever it is to figure out what this other number is. But sometimes 10 or 15 seconds, especially if you have to do a couple of these problems, starts to add up. So sometimes that's the difference between being able to answer an additional question before the time runs out. So that's just a test-taking tip. Now let's try to talk about how we have answered the question so far and how it's going to change moving into the next section. And this is extremely important. And that's this. Every single question that we've talked about so far, the statistic that we've used has always been X bar, right? Again, remember it's a statistic because it's a number that comes from our sample. So the number that's come from our sample that we've used to estimate our population parameter has always been X bar. And now, since we've used X bar, it's really, really, really important that we look at our sample size, little n. Little n had to have been greater than or equal to 30. However, what we're going to now do in our next section is that we're going to change this portion of it right here. We're no longer going to be doing X bar, but now what we're going to start to look at is we're going to start to look at the sample proportion. And we looked a little bit at sample proportions in chapter 6. And what we did for sample proportions is a little bit different. But let's take a look at the notes for the next section first. We're going to look at large sample estimation of a population proportion. So we're no longer looking at the population mean, but now we're looking at the population proportion. And in order to look at the population proportion, we have this following thing going on. Whenever we're trying to calculate out our confidence interval for the population proportion, we only have this one formula right here. And since we're dealing with large samples, the only thing that we're ever going to use right here is always going to be a z value. We're never going to have t values whenever we're trying to calculate out the confidence intervals for population proportion. Again, going back to our decision rule, even though it's slightly different now for proportion, remember that the only time that for the sample means that we ever got down to t values was when we had small samples. But here we're dealing with large samples, so we would never even get down to that box. However, and this is the main difference here, is this. How do we determine whether or not we have a large sample when we're dealing with proportions? And the way that we figure out whether or not we have a large sample when we're dealing with proportions is a concept that we talked about previously at the end of chapter 6. So let's try to jog our memory about that again. If we have a large sample, then what we would want to do is calculate out this interval right here, and this interval would have to lie completely between the interval from 0 to 1. If this interval that we calculate out here was not between 0 and 1, then we do not have a large sample. Our sample is too small. So this first example right here illustrates that concept. So let's use this example to jog our memory about how to calculate out whether or not we have a large sample when we're dealing with proportions. And it says this. So this is a confidence interval question for population proportions. To estimate the proportion of students at a large college who are female, a random sample of 120 students is selected. There are 69 female students in the sample. First, verify that the sample size is large. Then, if possible, construct a 90% confidence interval for the proportion of all students at the college who are female. And as always, interpret your results. So the first thing it wants us to do here is verify that the sample size is large. And how do we verify that the sample size is large? We have to calculate out this interval right here. So let's do it. We have an interval. That's this. Right? Just like we had on the previous page, we have an interval, but now we're using these square brackets. The lower bound of our interval is given by p hat minus 3 times the square root of p hat times 1 minus p hat over n. And the upper bound of our interval is given by p hat plus 3 times the square root of p hat times 1 minus p hat over n. So let's try to take whatever we can determine from this problem and plug it into this formula. Well, what do we know that we can plug in? If you look at this formula, there's really only 2 things that we need to plug into this formula. One of them is obviously p hat, and the other thing that we can plug in is little n, which is our sample size. So how big is our sample size in this problem? Well, here it says a random sample of 120 students is selected, so therefore little n is equal to 120. So let me plug in 120 into what we have up here so far. Alright, so there we go. Now if we know what p hat is, we can plug it into these remaining empty spots in our formula, and then we can do the arithmetic on it. So, what is p hat? Try to remember back to chapter 6. And p hat was our sample proportion. I think we also even looked at p hat in chapter 5, if I'm remembering right off the top of my head. But we definitely looked at it in chapter 6. But p hat stands for our sample proportion. So we're looking at the proportion of our sample. And here we're looking at the proportion of our sample that are female. So 69 out of 120 are female. So therefore the sample proportion is 69 divided by 120, which comes out to 0.575. Alright, so now we know that p hat is equal to 0.575. I can now plug that into these other empty spots for where p hat needs to go. And after I do that, now we're just right down to arithmetic. If you do the arithmetic on this left bound right here, or the lower bound, this is going to come out to 0.440, and on the upper bound, it comes out to 0.710. Alright, so let me ask you this. Is this interval our confidence interval? And the answer to that is no. This is not our confidence interval. The only thing that we've done so far is we've used this formula, and this formula only tells us whether or not our sample size is large. In order for our sample size to be large, this interval, the one that we just calculated out, has to be completely between 0 and 1. And is it completely between 0 and 1? The answer is yes. This is between 0 and 1, and therefore this is a large sample. So let me talk a little bit, just to make sure that we're all on the same page, of why this is between 0 and 1. And think about this here on a number line. Suppose that here I have a number line that goes between 0 and 1. The lower bound of the interval that we just calculated out is 0.440. If I wanted to mark 0.440 on this number line, where would I mark it? Well, 0.440, maybe it's like somewhere like right here. So I'll make it this bracket right here, since this is our lower bound bracket right here. So this right here is 0.440. If I wanted to mark down where 0.710 is, where would I mark down 0.710? Well, 0.710 is still between 0 and 1, so therefore my upper bound might be like somewhere like right over here. This is 0.710. So therefore the interval that we just calculated out is between 0 and 1. And if it's between 0 and 1, we have a large sample. So, if you remember back to our discussion in chapter 6, why does this have to be between 0 and 1? Well, we're dealing with proportions here. Proportions are like percentages of a whole. If we did this arithmetic, and suppose for a second that we got the number here for the upper bound to be equal to, I don't know, 1.2. I'm pulling that out of thin air now, right? I'm saying that instead of getting 0.71, we got 0.12. Well, now what we're saying is, think about what 0.12 means in terms of proportions. That's 120%. That doesn't make any sense, right? Like if I asked you what proportion of people in this sample were female, and he told me that 120% of people in the sample were female, that doesn't make any sense. The only time that it would make sense is if you gave me a proportion that was somewhere between 0 and 1. So 20% of people in the sample were female, or 80% or 90%. But if you told me something like negative 30% of the people in the sample were female, that just doesn't make any sense. So as long as we can do this arithmetic, and the arithmetic tells us that we're getting numbers that make sense when it comes to proportions, then we're going to say, all right, our numbers are good to go. We can consider this to be a large enough sample. If our sample is so small that we're getting whacked out numbers like 1.2, we need to go back and take a new sample, a larger sample. All right, so think back again to the discussion in Chapter 6. Here we're taking 3 standard deviations below p hat, and here this is 3 standard deviations above p hat. So as long as we're good to go for 99.7% of our data, making sense that we're getting numbers that work out for proportions, we're good to go. All right, so that was a long-winded explanation that I'm hoping is going to jog your memory about when we discussed this back in Chapter 6. All right, so far what we've done is we've answered this. First, verify that the sample is large. We verified that the sample is large. If we said that it was small, since this is the only formula that we have for confidence intervals, and that's for when the samples are large, if we came out and it said that it was too small, we just stop. The answer to that question then is it cannot be determined. We cannot go on. There's nothing else that we do. We're never going to use t-values in order to calculate out our confidence interval for proportions. So if we ever got the fact that it was small, we would simply just stop. The answer would be cannot be determined. But here we have that it's large, so it is possible to continue. So now what we're going to do is we're going to construct a 90% confidence interval for the population proportion. Now, how do we know that this is a Chapter 7 question? I should have started off this entire problem with that. But how do we know that this is a Chapter 7 question? And that is that it's asking us for a confidence interval. But now it's important to note that it's a confidence interval for proportions. Because how did we always start off our question or our solutions to confidence interval questions? We always started off with these 2 questions. Is n greater than or equal to 30, and is sigma known? But let's take a look at these 2 questions. The only reason why we asked this before, is n greater than or equal to 30, was to help us determine whether or not we were going to land in this bottom box over here in order to use t-values instead of z-values. But again, we're never going to use t-values for our confidence intervals for proportions. So we don't need to ask this first question. The way that we're really asking this first question right here is by calculating out this interval to see whether or not our sample size is large. The second question right here, is sigma known, did 2 things. The first thing it did again was help us determine whether or not we were going to be down here in this box. But the second thing it did was tell us what we were going to use up here in our numerator. However, if we look at the confidence interval formula for proportions, nowhere in here do we ever use sigma or s. So therefore, asking this second question is pointless. So therefore, when it comes to calculating out confidence intervals for proportions, we do not have to ask these two questions. Instead, so here, instead, I'm going to write, instead, we're going to calculate out what we had above in order to figure out whether or not we have a large sample size. As long as we have a large sample size, we can jump straight to this formula that we have above. So p hat plus or minus z sub alpha divided by 2 times the square root of p hat times 1 minus p hat over little n. Alright, so again, I'll repeat that. Whenever we're looking at confidence interval questions for proportions, we do not ask these two questions. Instead, we calculate out this interval above, and as long as this interval is between 0 and 1, we're going to say that we have a large sample, and we can jump straight to this formula for the confidence interval. If we're dealing with a confidence interval question for proportions, and we calculate out this interval, and it's not between 0 and 1, then we have a small sample, and we would just stop. Alright. So now we have a large sample, so let's finish off this problem and calculate out our confidence interval. We already know that our p hat from above was 0.575 plus or minus, I'll skip the z value here for a second. Here we have 0.575 times 1 minus 0.575 all over little n, and little n we already determined was equal to 120. If you do this, well, first we have to, I was going to say if you do this arithmetic, but here we still have to figure out what z sub alpha divided by 2 is. So let's do it together. We're looking at z values, so we know that we're looking at a normal distribution, a standard normal distribution. We have a 90% confidence level. The formula for a confidence level is equal to 1 minus alpha. Therefore, alpha is equal to 10%, which is just the same thing as 0.1. Here we're going to have 5% in this tail. Here we're going to have 5% in this tail in order to add up to 100%, which is the same thing as alpha divided by 2, since it's just half of alpha. So therefore, alpha divided by 2 is the same thing as 0.05. Now what we're going to do is we're going to use this alpha divided by 2, but instead of going to our z table, we're going to use this and figure out what our z value is going to be, but using our t table. So the column that we're going to go to, right, the subscript that we're using is 0.05. That's what alpha divided by 2 is, right? Remember, you can think of these things as being t sub alpha divided by 2. And our alpha divided by 2 in this problem is 0.05. So we're going to come to this third column again. Now, if we follow it all the way down to the bottom of the back side of our table, we're going to get that the z value, right? Remember that this last row right here in the third column are z values. So therefore, the z value that we're going to use is 1.645. We could find this z value again using our z table, but like I said before, you should become comfortable with how to figure out the z values using your t tables, as long as those z values are given on your t table. And again, if they're given, as long as the alpha divided by 2 in the problem that we're solving are the same as one of these subscripts up here. Alright, now, if you do this arithmetic, we get that this comes out to 0.501 to 0.649. And now, this is our confidence interval. So therefore, our interpretation for this is this. And that is, we are 90% confident that the true population proportion, proportion P is in the interval 0.501 to 0.649, which is what we just calculated out. Again, the only thing that's changing in this sentence is something that's in one of these three boxes. I think now we've gotten used to changing the first and the last box, but here now we're doing an example that we're no longer looking at the population mean mu, but now instead we're looking at the population proportion P. Alright, one last thing that I want to mention before we go on to the next part is this. This problem asked us to first determine, here let me scroll up a little bit here. Alright, here. This problem asked us to first verify that the sample size is large, then, if possible, to construct this confidence interval. Most questions that you're going to see that deal with proportions, confidence intervals for proportions, is not going to ask you to first verify that the sample size is large. If it asks you to verify that that the sample size is large, you have to do this top portion of the problem that we got done doing. If it does not ask you to first verify that the sample proportion is large, you can assume that it is large and just jump straight to this confidence interval formula right here. So let me say that again. If the problem asks you to first verify that the sample size is large, you have to do this first part up here. And if it's large, then you can continue to find the confidence interval. If you show that it's small, then you cannot determine the confidence interval. However, if the problem does not first tell you to verify that the sample size is large, you can assume that it's large. Skip this portion right here in the box and just go straight to the formula to calculate out the confidence interval. And like I said, most problems on the homework, on your exams, and also on the final exam do not ask you to first verify that the sample size is large. So therefore, don't waste your time doing all of this. You can assume that it's large and jump straight to this. If you do this for every single problem that doesn't ask you to do it, you're just wasting way too much time and you're not going to finish. Or you're just going to use a lot of time to solve your homework problems if you're doing that on your homework assignments instead. Alright, so let's go on to the next section here in the notes. And that says sample size considerations. So here, for sample size considerations, we're going to do stuff a little bit backwards. But why don't we do this? Why don't we stop this lecture video here, and I'll pick up this last portion in a very, very short lecture video the next lecture video. But for now, let's just call it quits here.